Problem number 4, we have an initial value problem, and we're going to use Green's theorem to solve for it. We have y double prime minus 6y prime plus 9y is equal to e to the 3x. And we have y of 0 is equal to negative 1, and y prime of 0 is equal to positive 1. So, the first thing we're going to do is to find the fundamental solutions. And for that we need the auxiliary equation, so we're going to turn our differential equation into a quadratic equation. We got m squared minus 6m plus 9 equals 0, and we have m is equal to minus 3 squared, so we have m is equal to 3 with multiplicity 2. Given that, we have our fundamental solutions e to the 3x and x e to the 3x. So we're going to solve for the homogeneous constants, and we do that by putting 0 in for x and taking the derivative and putting 0 in for x there as well. So in doing so, we're going to get constants c1 and c2. c1 is equal to negative 1, c2 is equal to 4. And so our complementary solution is going to be negative e to the 3x minus 4, or plus 4, x e to the 3x. And if this was a homogeneous differential equation, IVP, then we would be done. But it's not. It's non-homogeneous, and we got the right-hand side to equal e to 3x, so we're going to need to solve for that. Well, particular solution. So we will take y p, and we're going to solve for yp by using Green's theorem. So in order to use Green's theorem, we need the Wronskian, and remember our fundamental solutions are e to the 3x and x e to the 3x. So our Wronskian is going to end up being e to the 6x. And so now that we know the Wronskian, we'll use Green's theorem. We'll define Green's function, and then our right-hand side is e to the 3t. So our Green's function integral will look like this, and let's do some integrating with the appropriate limits. Let's take out an x e to the 3x from the first integral, so that's just going to be a 1 dt. And let's take out an e to the 3x for the second integral, and then it'll just have a t. And so all that just simplifies to x squared times e to the 3x minus 1/2 x squared e to the 3x, and that combines to just 1/2 x squared e to the 3x. Now that we have a complementary solution, we string that up with our final solution. And our final solution will be negative e to the 3x times 4 x e to the 3x, and then we got our particular solution, which is going to be 1/2 times x squared e to the 3x. Alright, so that's our final solution. Problem number 5 is our spring problem. We have a mass weighing 4 pounds attached to the spring is constant. It's 2 pounds per foot. The medium offers a damping force that's numerically equal to the instantaneous velocity. Mass is initially released at a point 1 foot above the equilibrium, so that's going to be an initial condition of -1 initial position. And a downward velocity of 14 feet per second. So that's going to be an initial velocity of positive 14. So first we need to find the initial value problem, and it says don't solve for the IVP, but I think we're gonna solve for it. It's easy enough to solve for. Alright, so what's our equation going to look like? Well, first we need to figure out some important constants here. So some of the important constants that for us might be important would be the mass and the spring constant. So, well, since we're dealing with pounds and feet, we need to look at the mass as a slug, and that's just the weight times the gravity. So the weight is 4 pounds and gravity is 32. Let's call it 32 feet per second squared. And so our mass simplifies to 1/8. Our spring constant is given to us as 2. So we're ready. We should be, our instantaneous velocity, our damping force is numerically equal to the instantaneous velocity. So that's just going to be a contribution of 1 times the instantaneous velocity, which is x prime. So using our formula, now we have to use a correct formula here. Let's keep the mass and the spring constant separate, and before going to that omega squared. So our formula is going to be m times the mass times x double prime is equal to, should be a negative spring constant here, negative kx minus beta, and beta is going to help us find our damping force, and our external force is f of x. And this particular problem, there is no external force, so we don't need to worry about that. So the negative sign here is adjusted, so we have mass is 1/8 slug. X double prime is equal to negative x, negative 2x, the 2 is our spring constant, and then our damping force is just going to be x prime. We have no external force, so let's call that 0. So our initial position is -1. We're a foot above the equilibrium, and our initial velocity is 14 feet per second. So we take a look at our differential equation. Just, you don't need to, but you can rewrite it so that it's in standard form, and that might be easier to factor our auxiliary equation. So our auxiliary equation is going to be m squared plus 4m plus 8 equals 0, and so we got a solution of -4 multiplicity 2. That means our fundamental solutions are going to be e to the negative x, e to the negative 4x, and then our second solution would be x e to the negative 4x. And so our general solution will look like this, with the constant c1 and c2, and then we're going to use our initial conditions to solve for them. So first we're going to take the derivative, and then we're going to put 0 in. Putting 0 into the position equation, we get c1 is equal to -1. And remember that our position says that our initial position is at -1, so c1 is going to be -1. And then putting our 0 into the derivative, we're going to get -4 times c1 plus c2 is equal to 14, and so that gives us c2 is equal to 10. Well, we have our constants solved for, and so we should get our solution. And our solution is going to be -1 times e to the negative 4x plus our c2 is equal to 10 x e to the negative 4x. Alright, so that's our spring problem.